Hello, welcome to lecture 25. In this lecture, we're going to do a little bit more on magnetic flux, then we're going to discuss Lenz's law and Faraday's law. This is kind of an interesting magnetic flux example. We have a rectangular loop 20 centimeters by 40 centimeters, but it's in two different fields. On the left-hand side, the magnetic field is into the page, and on the right-hand side, it's out of the page. So one way we could approach this problem is if we found the net magnetic flux on the left and the net magnetic flux on the right. If we add them together, we get the total magnetic flux. Okay, let's remember our equation for magnetic flux. It's B dot A, so the area vector dotted with the magnetic field vector. We know that an area vector is perpendicular to the plane of the loop. So our loop is in the page. It means the area vector is either into the page or out of the page. The problem doesn't say which. I'm going to assume into the page. And if the problem doesn't say, you should make sure that you show what your assumption is very clearly. Okay, so it's into the page, both on the left and on the right. Whichever way we choose, we need to make it the same on both sides. Okay, let's go ahead and find the flux now for both sides. On the left, it's B dot A for the left equals B times A times the cosine of the angle between them. They both point into the page, so that angle is zero. So the flux then is the magnitude of the magnetic field, 2 teslas, times the area. So the left-hand side is a square of 20 centimeters, 0.2 meters times 0.2 meters. 2 times 0.2 times 0.2 equals 0.08 Webers. Okay, that's the magnetic flux on the left. Let's also do the magnetic flux on the right. So same deal, it's the field on the right dotted with the area on the right, which is B times area times the cosine of the angle between them. The area is into the page, the field is out of the page, that angle is 180 degrees. Okay, so the strength of this field is 1 Tesla. We're multiplying that by the area, which is 0.2 meters times 0.2 meters. Cosine of 180 is -1. So 1 times 0.2 times 0.2 times -1 gives us minus 0.04 Webers, or Teslas times meters squared. Okay, that's the flux through each side of the loop. Our total magnetic flux then is what we get if we add those two guys together. That turns out to be equal to 0.04 Webers. That's the net magnetic flux through that loop. That our net magnetic flux is positive, it means there are more magnetic field lines which are parallel to the area vector rather than anti-parallel. If more lines were anti-parallel, then it would be a negative flux. This is another problem where the loop is broken into two pieces. I'm going to leave you to try this one as a homework problem. I won't make a video, but I will write up and post the solutions. Okay, let's move on to an example that's probably a little bit more challenging. We have a loop 1 centimeter by 4 centimeters, and it's 1 centimeter away from a long straight wire which is carrying current. We'd like to find the magnetic flux through the loop. So let's think about that current carrying wire. We know that the current carrying wire makes a magnetic field, which is equal to mu naught I over 2 pi r. The direction of the magnetic field, we see in our picture that the current goes down. We know that the magnetic field around our wire makes big circles. To find the orientation of the circles, you make a circle, you put your thumb in the direction of current, circle with your right hands. You ask, what are your fingers doing on the side where the loop is? Your fingers should be coming out of the page towards you. So the magnetic field over here is out of the page. Just scribble in our diagram. We'll neaten it up as we go. So the direction of our field is out of the page. Now the other thing that's important about our field is that it depends on r. It depends on the distance away from the wire. So that tells us that the magnetic field where the loop is not constant. So B is variable. What that means is that when we do our magnetic flux expression, we can't just do B dot A because B is variable. We have to use the integral expression. Magnetic flux is the integral of B dot dA. We will, of course, incorporate the dot product, B times, magnitude of B times the magnitude of dA times the cosine of the angle between B and A. Okay, so we know what to fill in with B. It's mu naught over 2 pi r. We're going to have to figure out what to fill in for dA, and we're going to have to figure out what's theta. Let's just go on to the next slide to work on those parts. For our next step, we have to identify what do we mean by dA. So dA is a little bit of the area of the loop. It makes sense to pick a little area element that's a long, thin strip. So there's no variable in the y direction. The magnetic field doesn't change in the y direction. It only changes in the horizontal direction. So we'll say that the distance to our loop is r. That's a variable. And the area of our loop, it's a little bit of area. I'm going to say that the direction is out of the page. So there's dA. I have to choose either into the page or out of the page, and I'm going to choose out of the page. So our area is a vector. We've already settled on the direction. Let's put in our coordinate system, x, y, and z. So the direction is in the positive z direction, or k hat. Why don't we get some of these notes down? So dA is either in or out. I'm going to choose arbitrarily because we can't tell which way. So I just choose out because I had to pick. The magnitude of dA, well, it's just a rectangle, so it's length times width. The length is given as 4 centimeters. I'm going to label that as L. And the width is a little bit in the horizontal direction. There's my width. So my horizontal direction is in the x direction, so dx, so times dx. The last thing I'm going to do is put in my origin. I'm going to say at the wire is x equals 0, so therefore our x coordinate is the same as our r coordinate. So that's an extra little bit that we figured out. X equals r and dx equals dr because x and r are both referenced to the same origin and they're in the same direction. Okay, now we have something to put in for b, we have something to put in for dA. The last is our cosine theta. B is out of the page, dA is out of the page. That makes theta equals 0 degrees. Let's put these things in and see if we can solve for our magnetic flux. We're ready to put it all together now. So our magnetic flux is the integral of b, which is mu naught times I over 2 pi r. Remember, r and x are the same thing, so I'm going to put that in terms of x, times dA. dA is equal to L times dr, or L times dx. And cosine theta is cosine of 0 degrees. Okay, so for our next step in the integral, I'm going to take my constants outside. Mu naught times I times L over 2 pi. Left with the integral of 1 over x dx, and I've put in that cosine of 0 is just equal to 1. Okay, I need the limits of my integral. Well, the limits are going to be the x limits of my loop. So my loop starts on the left with a distance of x equals 1 centimeter, and my loop finishes on the right with a distance of x equals 2 centimeters. So the limits of my integral are from 1 centimeter to 2 centimeters. I'll put that in terms of meters. Okay, the integral of 1 over x dx, that's the natural log of x. So I can fill that in. That's evaluated at the limits. So I get mu naught times I times L over 2 pi times the natural log of 0.02, subtract the natural log of 0.01. When you subtract logs, you're allowed to divide the argument. Mu naught I L over 2 pi times the natural log of 0.02 divided by 0.01. Okay, from here, it's just a straight up plug and chug. Mu naught is equal to 4 pi times 10 to the minus 7 Teslas meters over amps. I is the current, that's given as 1 amp in the picture. L is the length of the loop, that's 4 centimeters, 0.04 meters, and then we have pi in our digits. Okay, put all that through the calculator, and what we get is 5.55 times 10 to the minus 9 Webers. That's the magnetic flux through that loop.